Log on, tune in, find out. Another good idea from Cambridge.
Gábor Lugosi from Barcelona. You will speak on Charles threshold for percolation on Discrete. Thank you very much.
It's a pleasure to be here. So thanks a lot for inviting me. I'm gonna tell you a little bit about a work that I've been involved with these people: Itai Benjamini, Stefan Bushron, and Raphael, who's sitting somewhere here. And this is about random graphs. So let me start with showing you a few pictures. So this is an Erdős-Rényi random graph. So of course, Erdős-Rényi were the first to study systematically random graphs, and their model is that we have n points. Now I just threw them down on this plane, and we connect two independently at random, independently of each other with probability p. And they studied what happens as p grows, and they discovered that many interesting properties are born. Happen all of a sudden. There are many interesting properties that up to a certain edge density don't exist, and all of a sudden then they will exist with a huge probability. So here's an illustration. So we start throwing in edges, and different components are different colors. So you can see that at the beginning we have many very small components, and then you see here still we have lots of small components. The largest one is still of logarithmic size, and then all of a sudden there's a giant component that's born. So this is probably the most interesting phenomenon that they discovered, that there's this sharp transition when all of a sudden a giant component is born, and so there's one big component and all the rest are very small. And then as we keep adding edges, the smaller components become even smaller. At the end, the graph will get connected. So this happens around, and the probability is log n over n. The big component, the giant component, is born when the probability of an edge is 1 over n. Okay. So this is what it looks like. This is the size of the largest component in this example. So you can see that there's a sharp transition. The largest component is very small, and all of a sudden we have this huge component that contains basically everything. But this phenomenon occurs in other graphs, not only the Erdős-Rényi random graph. So this is a random geometry graph. So here we have n points thrown at random on the plane, and we connect two of them if their distance is less than a threshold r. So there are already some edges here. These are the points that are really close to each other, and now we start growing. This threshold, so more and more edges will be born. See? Here, a very similar phenomenon occurs. Lots of small components scattered around, small components, and boom! All of a sudden, there's one giant component that's born. So the random geometry graphs have again the same kind of threshold phenomenon, that from lots of small components, all of a sudden there's a unique giant component that's born. And then as we keep adding edges, at the end basically everything apart from a few isolated vertices are connected, and then the graph becomes connected, and as we keep adding edges the graph becomes very regular. Now here's another example. So this is an example that was studied by Itai, Komlos, and Szemerédi in 82. So they said that let's look at the vertices of the d-dimensional hypercube. Okay, so these are the 128 vertices of the 7-dimensional hypercube projected randomly in 2 dimensions, and now we keep adding edges.
Projected linearly, but with a random linear projection.
Sorry?
Projected linearly, but with a random.
This is a linear projection. A linear random projection, yeah, just to illustrate. And we start adding edges, and again, the very similar phenomenon occurs. You can start seeing the structure here, but all of a sudden, again, there's one giant, the big red component that's born here, and everything else is small.
These are random edges of the hypercube.
These are the random edges of the hypercube. And this transition occurs according to their result when the probability is about 1 over d, 1 over the dimension. And again, if you keep adding edges, then you will get a very regular graph. And this is, again, the size of the largest component. Very similar phenomenon. So the question, these are, of course, very, very different kinds of graphs. The Erdős-Rényi random graph, a random geometry graph, the random hypercube. So the question is, what are the graphs such that we have this phenomenon, that there's a unique giant component that's born all of a sudden? So this is the general question, and this is what this talk is about. The talk doesn't cover any of these examples. So but we are trying to get some general understanding of for what kind of graphs do we have this type of phenomenon. And we follow the footsteps of Alon, Benjamini, and Stacy, who started to look at expander graphs. And so this talk is about expander graphs and this percolation model. So we start out with a finite graph. That's our basis graph, and we delete every edge independently with probability 1 minus p. Or in other words, every edge, we put down every edge of this finite graph with probability p independently of each other. And we wanna understand what happens. How does this graph behave as p grows? And the main question that we are interested in about is what happens? Is there a giant component? How many giant components are there? Where is the threshold? When do they appear? Is there a sharp transition? So these are the general questions that we are interested in. So of course, if G is the complete graph, that's just the Erdős-Rényi model. And that's of course very well understood. If G is the hypercube, then that's the example of Aitai, Komlós, and Szemerédi. Yes?
You'll assume the degree is bounded somehow, or
we will assume that the degrees are bounded.
that's why they are not covered.
Exactly. So, this phenomenon is also very well understood when the underlying graph is a random graph, is a random regular graph. So these are sparse graphs that every vertex has the same number of connections, so has the same degree, and we pick one randomly among all those graphs. So these graphs will be expanders with high probability. So what we are trying to look at is just assume that the graph is a bounded degree expander. Okay, and this is the type of graphs that Alon, Benjamini, and Stacy considered. So. So what does it mean that the graph is an expander? Well, we look at the edge isoperimetric number, a Cheeger constant. So this is just we look at all sets of vertices that have that contain at most half of the edges, half of the vertices, and we look at how many edges go out of this set. And we look at this ratio. Okay? So since we assume that every vertex has a bounded degree, the number of edges will be at most linear. So it makes sense to look at this constant, and we will assume that this constant is large, is bounded away from 0. Okay, so this is our main assumption. So we're looking at giant graphs, huge graphs that have a bounded degree. Every vertex has a bounded degree, but they have this expansion property. Okay. Okay. So what does it mean that a component is giant? Well, it means that it contains a linear fraction of the vertices. Okay. So that's our main question. And Alon, Benjamini, and Stacy proved under just these two assumptions that there's at most one giant component. No matter what p is and what the underlying graph is, there cannot be two giant components. So either there's none or there's one. Okay, And basically this follows from the expansion property. So if there were two, then the probability that they connect up would be so big that it will never happen that they can exist without each other. So what they proved precisely is that the second largest component is at most of this size, n to the some power, and this power is strictly less than 1, depending on these two constants, the bounded degree constant and the Cheeger constant. Okay, and there's no symmetry assumption about the graph. This graph can be completely arbitrary. They also proved that the giant there is a unique giant component that's born at a certain threshold, but for this they needed to assume they needed to assume two regularity properties. So one of them was that every vertex has the same degree, so the graph is d-regular, and the other was that these graphs locally look like trees. So the girth is the girth of a graph is the length of the shortest cycle. So if the shortest cycle is very big, then it means that locally these graphs are very tree-like. Then there is this the same type of phenomenon that's well known from the Erdős-Rényi random graphs. So if and they can, in this case, they can identify the threshold. So this is the main reason why they need to assume that the graph is d-regular. So if p is greater than this threshold, 1 over d minus 1, this is a constant, then there is for every p greater than this, there exists a c such that the probability that there is a component of size c times n goes to 1. It's very large. And if p is less than this threshold, then there's no component of size c times n for any c. Okay, with large probability. So the question is, are these necessary? Probably not.
Also, does C have a nice formula in terms of P?
C, no, there's no nice one that I know of. At least not under these general conditions. So, so the question is, can these two conditions be removed? Of course, if we remove the irregularity, then we can't really hope to identify the threshold, but we can still.
Average degree.
Sorry?
The average degree would be.
Maybe. I think that's a very bold conjecture.
Yeah, you could have two different parts of the graph, one very dense and one
Exactly.
very
So
sparse, and
yes,
the
So
average wouldn't be a good.
it's more like the smallest.
That's the would be
Yes, it's true. So, so here's like this conjecture. We can't prove this. So what the most general result that we would like to see is that is it true that for any expander, for any sequence of such graphs, there is a sequence of thresholds such that if Pn is greater than the threshold by more than epsilon, then there exists a C such that there is a component of size C times n. If P is less than this threshold, then there's no giant component. Okay. So instead of this, we look at. Oh, by the way, this was established under regularity assumptions, and these are kind of a different type of regularity assumptions. Benjamini, Nachmias, and Perez showed that if the graph converges to an infinite bounded degree expander, then this type of behavior holds. So what we look at is what happened. We look at a fixed fraction. So what we're interested in is does there exist a component of size n half? Or does there exist a component of m-fifth? Okay, so we're looking at a fixed of a given proportion of the vertices. And we can show that these are born. There is a threshold phenomenon for these. Okay, this doesn't imply this more general conjecture, but it shows that for every C, this probability that the graph contains a component of size c times n, this has a sharp threshold. This we can show, and that's the theorem that's written here. So for any expander, so expander now means bounded degree expander, and for any c between 0 and 1, there is a sequence of thresholds, and which depends on c, on the proportion that we are interested in. For every epsilon, if Pn is greater than this threshold plus epsilon, then the graph will contain a component of size c times n, and if Pn is less than this, then it won't contain. Okay, so then we do have a sharp threshold. So how does the proof work? So probably I should emphasize that these numbers are strictly bounded between 0 and 1. Okay? So this is why we can talk about a sharp threshold, because these probabilities cannot be too close to 0.
So if you took the limit of this as c goes to 0, is this what you were interested in the previous?
So in principle, this theorem doesn't exclude the fact that these change very slowly with c. So there should be a threshold such that below that there's no component of any constant size.
The amount that p star n of c is bounded away from 0 depends on c?
Yes, it does. Well, actually not. No, it doesn't. It doesn't.
Oh,
This is always at least 1 over d. Okay. I will show you how.
Oh, wait, and your graphs were the d regular in the previous, so in your theorem? Are these regular graphs?
No, they don't have to be regular. These are.
So should there be some parameter expressing an expansion in the result? I mean,
of course, these will depend on the expansion constant and the degree. Where the threshold is, this will depend on it.
And the speed with which the probabilities go to 0 depends on the nature of the
Of course, yes. So everything depends. So B and D, the two constants are fixed here. Okay, and then we take the limit.
so it can be stated essentially as a theorem about a fixed graph and not as a sequence?
Yes, of course. So this is for big, large expanders. Okay, and so you can state it that if we have a large expander, then there exists a threshold such that this probability will be close to 1. What does and how close? Well, that depends on the size. Okay. Yes. This is basically about fixed graphs. It's the sequence just. Yeah. Okay. So the plan of the proof is this. So first we will show that the value of p at which this probability is exactly 1/2, so that's the critical probability for this event to occur, is strictly bounded away from 0 and 1. That will be our first step. Now, if the graph was transitive, then we would be done, because the general result of Friedgut and Kalai tells us that if you have a function, a sufficiently symmetric function, if you have a graph property, that means that if every influence of every edge is the same, then you have a sharp threshold. And all you need is that the critical value is bounded away from 0 and 1. But it's not. So we don't want to assume that the underlying graph is transitive. We just want to look at arbitrary expanders. So we need to work a little bit more. So what we will do is the following. So first we will show that around the critical probability, where this explosion, when this happens, the derivative of the expected size of the largest component is large. It's proportional to n. So the derivative is large. It's proportional to the number of vertices. And then one that's done, all we need is to show that the size of the largest component is concentrated. And I will show you how these two facts imply simply that there is a sharp threshold. Okay, so we have these three steps. The first step, well, this is where we need a little bit of graph theory. Most of these arguments were worked out in the paper of Alan, Benjamin, and Stacy, but I will give you the hints. Basically, for the fact that P is bounded away from 0, it's enough that the graphs have bounded degree, and the fact that they are bounded away from 1, that's where we need that the graph is an expander. Okay, and for the second step, we will use Rousseau's lemma. And for the first step, we will use inequalities for the variance that are that come from this Fourier analytic, the hypercontractive estimates. Okay. All right. So so let P and C be this critical probability. Okay, so Ln1 is the size of the largest component, so we just look at the probability that the largest component is at least C times n. That's when this equals 1/2, that's the critical probability. Okay. So the fact that this is bounded away from 0, it follows from a standard branching process arguments, and this is this probability will be always at least 1/d-1, simply because we have a bounded degree graph, and the branching process will die out if the probability is less than this. Okay, so there can't be large components under this probability. This is very standard. How do we show that the critical probability is bounded away from 1? Well, this is where the expansion property comes into play, and at several points. So the first step is to show that for any vertex, if you look at the size of the component of that vertex, then if P is big, really close to 1, this big, then the probability that this component has at least half of the edges is not negligible. It's at least some constant, and this follows from the expansion property, because if this component was smaller than half, then because of the expansion property, it would have lots of connections to the exterior, so its boundary would be large, and one of those edges would have to be there. So then we can just look at the sum of the indicators that the size of the component is greater than some large constant. Okay. Now, because of this, the expected value of this random variable is linear, and if R is a constant, then these are not independent, but their dependency graph is sparse. So we can use Janssen's inequality to get an exponential concentration bound for this indicator, for the sum of these indicator functions. Okay, so this is the number of vertices that are contained in components of at least this size, R. Okay, R will be a large constant. Okay. So this is.
This is essentially a Thales argument.
Sorry.
This is a Thales argument.
This is a
Thales.
Thales.
Tail.
No, Thales. P-E-I-E-L-S. Okay.
No, it's not the
No.
He says no. it's a simple argument. Okay, so but then we have so what this says is that with large probability, the number of vertices that are contained in these not too small components is large. So because of then we can use the expansion property to show that this will connect up. So the way to do this technically is to keep a little probability out of our total probability, and now superimpose another random graph with a very small edge probability, and that will connect up these small components with large probability. Okay, so this is why the threshold is near 1, is bounded away from 1. Okay. In fact, you can show that that for every C1 which is less than 1/2 and C2 which is greater than 1/2, there exists a Q such that if P is greater than this probability, then this random graph cannot contain a component of this size between C1 and then C2n. Okay, so the largest component will be either very close to 1 or either very close to n or very small. Okay, and then we have these exponential tail bounds like this. Okay, so now we know that the threshold is bounded away from 0 and 1. So now we want to show that that there is this sharp threshold. So take a monotone function on the hypercube. Okay, so the dimension of the hypercube is now the number of edges. These are our random variables that we throw in. So we have, if we have any monotone function, monotone means that it's monotone in every coordinate. Then a very simple argument that well, this is basically a simple generalization of Rousseau's lemma. Rousseau's lemma concerns Boolean functions, but it's easy to extend it to arbitrary functions. This was observed in Raphael's thesis. So if you look at if you look at the expected value of this function under probability P, so that this means that every this means that we put on the product Bernoulli distribution on the hypercube, and we look at the expected value of this monotone function under that distribution, then the derivative of that equals this expression. And then what we have here is the sum over all edges or all coordinates of the expected value of the absolute value of this quantity, and this quantity is just the difference between f and the conditional expected value of f. We take the expected value only with respect to this edge, to this one coordinate. Okay, so this is like the influence. So we look at the average influence of this one edge. Okay, so by how much can the function change if we flip this edge? If we put this edge in and take it out, we look at the expected value of that and how much that differs from the actual value of f. Okay, and so this is the L1 norm of this random variable. Okay, and so we will use this for when f is the size of the largest component. Okay, so as I said, what we want to prove now is that the size of the largest component around the critical probability grows quickly, has a derivative which is linear in the number of vertices. Okay. Okay. So Rousseau's lemma tells us that. So remember, it says that we can this derivative. So this is the derivative of the expected value of the size of the largest component, the derivative with respect to the probability, equals the expected value of the absolute value of this delta E. So if I just take the negative part, then of course this is a lower bound. I can rewrite this as, so this is the negative part of the value of the function, and what happens if I flip the edge E. Okay, so if it was there, I take it out. If it wasn't there, I put it in. So I look at the negative part. So what does that mean? That means that I want to look at when by flipping an edge, this function increases. Okay. So but when can this function increase? It can only increase if that edge wasn't there, and it can only increase if that edge was on the boundary of the largest component. If the edge that we're looking at is not in the largest component, then there's no way that the size of the largest component will increase. Okay, so so this derivative is lower bounded by the expected size of the boundary of the largest component. Okay, but we know that the boundary must be large because we are close to the critical value. So we know that the size of the expected size of the largest component is large. So that means that it will have to have a large boundary as well, because of the expansion property. So that means that this derivative is bounded from below by a linear function, by a constant times n. Okay? So this seems to looks like a very loose bound, because all we look at is that if you take an edge which is on the boundary, then if we add it there, then the size of the largest component can increase, will increase by at least 1. So of course, in many cases, it may happen that you add larger components by adding an edge, but this is a very simple lower bound. Okay. So now we know that the derivative of the size of the largest component grows quickly. So so this little argument here will tell us that that if we can control the variance, the concentration properties, in a very weak way of the size of the largest component, then this will guarantee that we have a sharp transition. So how does this work? So P is the critical probability. So remember, that means that the probability that the largest component is at least Cn is 1/2. Okay, so this is our critical probability, and let's look at a value which is a little bit smaller. Okay, so what we want to show that the probability under this smaller Q that the largest component is large will be very small. Okay, so we want to show that there's a sharp threshold. So if we go a little bit below the critical, then this probability goes from 1/2 down to 0. Okay, all right. So let's look at this probability. So what I do here is that I add on both sides the expected value under the same probability, under Q, the expected size of the largest component. Okay. Now C times n is what? This because of the definition, this is just the median of the size of the largest component under the critical probability. Okay. So the C times n equals the median. Okay. So now I add and subtract the expected value of the largest component, of the size of the largest component in the critical. Right? So now here I have the difference between the median and the expected value, and here I have the difference between the expected value of the largest component and the expected value of the largest component under Q. Okay? Now the difference between the median and the expected value for any random variable is less than the standard deviation. And so I need a bound for the variance of the largest component under P, and then if I can show that this is sublinear, then because of the previous result, because we know that the expected value grows quickly, we know that this difference is at least C times. This is like epsilon n, right? Because we know that the derivative of this quantity is proportional to n. So we know that this is large. So if I can show that the variance is subquadratic, if the standard deviation is sublinear, then this will be negligible. And what I will need is to show that the probability that this guy is greater than constant times n is small. But for that, I will use Chebyshev's inequality. And again, I will need a bound for the variance of this, but now under Q. So I need a bound for the variance of the size of the largest component under P and under Q, okay, under both probabilities. But this can be done by the same argument, which is by these variance inequalities. So I think here I should say the Poincare inequality tells us that the variance of any function of the hypercube is bounded by this quantity, where this is just the sum of the expected values of this delta epsilon squares, right? So this is just the condition, the expected value of the conditional variance when we take the variance with respect to the edge. Okay, so this is a Poincare inequality, but this is not quite enough for us. So we need an improvement, and this improvement, well, there are various inequalities in this family. Talleyrand had one in '94, but what was most convenient for us was this very nice inequality by Falik and Samorodnitsky, who show that we can improve on Poincare inequality if the ratio of this E2 and E1 is large. Okay? And then we can get a logarithmic improvement, but that will be enough for us. Okay? And what's this E1? Well, it's just the sum of the squares of the expected L1 norm of these increments. Okay? Okay, so combining this inequality with Rousseau's lemma. Remember, in Rousseau's lemma, we also have exactly these quantities appearing. So if we combine the two, then it's easy to see that the variance under P or under Q, it doesn't matter, is bounded by something which is, we have the just derivative of the expected value of the largest component n times n divided by log n. So remember, this is about linear in n. So we have, this is like n squared over log n. We get something. Okay? And this is enough. So this is looks like a very innocent improvement when you look at these type of inequalities, but this logarithm helps a lot.
That's what leads to this log n there, or no?
That gives us the log n here. So if we put everything together, then what we see is that okay. So let P and alpha C be the probability at which the probability that the largest component is at least C times n is exactly alpha. Okay, so these are the quantiles of this random variable. So what we have now is that if alpha is small, then the distance between when this probability is very close to 1 and when this probability is very close to 0, is very small. Well, it's very small. It's smaller than it goes to 0 with n. This very, very slow place. But we know that these quantities are bounded away from 0 and 1. So this means that the threshold is sharp. Okay. So the size the components of size C times n will appear in intervals of at most 1 over third root of log n. Okay. So this is a very weak bound, and of course we know that for example for random deregular graphs, much faster transition is known. So this is a really weak result, and I wonder how one can.
It's on the supercritical side. Ah, okay. Like
So even if the underlying graph is transitive, then even the Friedgut-Calais result gives us a 1 over log n threshold width. So this is really weak, and I'm wondering if one can do better. Another direction in which it would be very nice to strengthen these results is to weaken the expansion property. So, for example, in the d-dimensional hypercube, we don't have this expansion property, but almost. So, or if you look at the grid, standard percolation, we have some kind of expansion property. So, my wild conjecture would be that what matters is expansion, but something much weaker should be enough than what we need here. So we work and we heavily use the fact that the expansion constant is bounded away from 0, but maybe if that constant is n to some power, you can still do something. But I have no idea. So it would be very nice to understand really what gives us these the most general conditions under which the giant component appears in such a way, and that's it.
Questions?
So the adjust parametric number of the hypercube isn't bound away from 0, but isn't it 1? Or so what's the adjust parametric number for the hypercube? Isn't it 1?
I think it normalizes it by the degree.
Okay.
Oh yeah, yes, of course. Because then you don't have a sparse graph anymore. So okay, my conjecture is for sparse graphs. So for bounded degree graphs. For denser graphs, I think it's a different story. Yes.
So there's some. Can you explain maybe why your method doesn't prove the the original conjecture that you mentioned? Because it seems that you defined this Pn star, and then you can show that at this Pn star the expectation grows very rapidly, but also that there is concentration of the largest component. So you know that right after there is a large component. But it seemed that you also, maybe I didn't catch that, but it seemed that you also can prove that before there is no giant component.
But what matters before and after that depends on C in our result.
Before there is no component of size larger than Cn, but there might be a component of size C over 2.
Yeah. So maybe I missed something in the proof.
Yeah. So for us, in all our results, this thing depends on C.
So maybe can you move back to a couple of slides?
Okay.
Yeah, I think it was just after that one.
Here?
Yeah. I see. So I missed the.
Okay.
More questions? Or if not, thank the speaker again.